the example that I'm going to take you through is an example of how to evaluate somebody's credit, whether it's good or bad. And that might be similar to customer churn, because essentially what you're doing is you're trying to classify whether customer will churn sort of 1 or 0. So obviously there's certain characteristics that might predict customer churn. For instance, when have they last paid? When have they last logged in? How long have they been a customer? So all these would be considered features that you'd feed into the model in order to do your prediction. So the example that I'm going to take you through is around credit, where the features are, for instance, how much credit are you applying for? Are you employed, yes or no? Do you have your own house? Do you have a savings account? So those are the sort of features that I'm going to sort of walk you through in this example. But think about your particular problem that you want to solve and how those features can actually sort of be replaced into the same idea as the credit model. So with that in mind, so there's a couple of components when you want to do machine learning and AI. So obviously you need the data, and your data needs to be as good as what it can be. So what we do is when you connect OQLIS to your data set, we actually run that data set through a health check where we determine if there's any missing values or duplicate values, and we calculate then a data health that will allow you to either improve your data or fix any errors that are present in your data. So what you'll see over here is that I've got a couple of data sets loaded up, and the particular data set we're going to look for is the credit data set. Now, when you connect OQLIS to your data set, we run that through a data profile. So what the data profile allows you to do is to assess the high-level statistics and more descriptive statistics that sort of describe your particular data set. So as an example, one of the variables in my data set is the duration of credit. And in this example, I can see the distribution of that, of the data set's duration. And I can also see, for instance, this next column is a categorical column that deals with credit history. So is that person, are all their credits paid? Do they have no credits? Have they delayed previously? Are they critical with other providers? So these are all my variables or my columns on my left-hand side. And we then calculate descriptive statistics that help you make sure that this data set is actually modelable. So that's the first step of doing this machine learning or an AI process, is getting your data right. So that's the first step, data health, data profiling, to make sure you've got all your features correct. And then the next step is to actually feed that through our AutoML engine. So what the AutoML engine does is it passes that data set through a series of algorithms that are sort of the best-in-class algorithms for that particular problem set. And it runs through a tournament-based methodology where it calculates specific accuracy and different metrics that help you evaluate what algorithm is actually going to best suit that model. And obviously, the thing that we want to drive is highest accuracy. So basically, the way to set that up is if you had to start from scratch, you'd connect your data set up, you'd make it available for the AutoML. Then what you do is you'd create a new AutoML problem, and you give it a name and you give it a problem type. So right now, your particular problem type would be a classification problem. So I want to predict whether a customer will churn 1 or 0. That's a classification problem. So what I'll do is I'll say, okay, cool, this particular AutoML model will be churn, and I'm going to then pick my churn data set if that's connected up. So once that's all connected up, what happens is you get to set up how the AutoML will run. So the first step is to determine, well, what do you actually want to predict? So in this example, my thing that I want to predict is the class of credit. But in your example, that'll be, for instance, the column churn, which is a 1 or 0. So in this example, I'm trying to predict the class of credit. I'm telling the system that I want to do a 60-40 split in terms of 60% of the data on training, 40% on testing. So my accuracy is actually going to be calculated on my 40% testing data. And then we also do some unique calculations in terms of measuring potential overfit risk that I'll talk about at a later stage. But basically, what you don't want the model to do is fit very well to your training data set, but fit poorly to your testing data set. So that would be an example of something that's overfitting. So the model hasn't generalized very well, but I'll show you how that calculation takes place. So once all of this is set up, you can then specify what column types are these particular features. So by default, we do some inference based on the actual underlying data. But if, for instance, we got the inference incorrect, you can actually then change whether this is a numeric column, a categorical column, a Boolean text, or date. And then the AutoML will actually treat that column as that data type. And then also you can opt to use some of these features or not. So you might have a data set that's got 20 columns, but you might only want to use 15. You can then just set those columns to inactive, and the model actually won't use those columns. It'll actually ignore it. And then further down, we just highlight some more descriptive statistics on top of that data set, just to make you a little bit more informed in terms of what is the best choice for these particular data types. So then once all of this is set up, we do a lot of this inference for you. But once all of this is set up, you basically hit run experiment. And what that's going to do is that's going to fire off a process to the OQLIS AutoML server that's going to run this data set through the series of algorithms to try find the best fit. So we'll just let this run for a couple of seconds, and there we go. Our first algorithms have come out the leaderboard. And right now what we're seeing is that the logistic regression algorithm is currently winning in terms of an accuracy of 74.6%. And then in terms of what I mentioned earlier around overfit risk, what it's doing there is it's calculating the difference between the score on my training data set and the score on my testing data set to make sure that I'm not going to pick an algorithm that tends to overfit and not generalize very well. So in this example now, my logistic regression is winning. And then I can see the high-level view on what's actually happening within this model. So over here in the center, I can see my confusion matrix. So what this is describing to me is that this model is able to predict bad credit with an accuracy of 80% and predict good credit with an accuracy of 70%. So basically, if you pushed your churn data through, this leaderboard will then be able to tell you to what degree of accuracy can the model actually predict that churn. And then also what we do is we calculate the most important features that the model is considering when making a particular decision. So in this particular example of logistic regression, the fact that somebody has no checking account is very, very important to this model, and also whether somebody's a foreign worker or not. And then also what I can do is if I want to evaluate the detail of the other models, I can actually just click on the other particular algorithms, and that's going to give me the detail of those particular algorithms. So if, for instance, I might want to not use my most accurate, but I might want to use another one for another particular reason, I can actually go ahead and evaluate the performance of each one of these algorithms. So once I'm satisfied that my algorithm has generalized my data set very well and is able to predict, basically what I can do then is go ahead and train my model. So once that model is trained, it's basically going to run through a training step again. It's going to then make my model available for deployment. So what I'm going to do is I'm going to just jump to a previously deployed credit model that I've got over here. And this is my deployed logistic regression model. And then once again, we've got our statistics of what's happening in terms of its ability to make a prediction, all the high-level metrics that we've calculated. But then we take it one step further to say, well, I want to understand a little bit more about how this model is actually making decisions. So what we do is that we've built explainability into the process. So for instance, if I want to evaluate dependence plots, which basically allow me to get a global view of what the model is finding important and the degree to which it's finding certain variables important. I can go ahead and evaluate those particular variables and the impact of the model against those variables, and I can see that both for numerical and categorical. So for instance, if I find that the model is able to predict churn with 95% accuracy, I'd be able to go ahead and see within the model what is driving the accuracy of my prediction of churn. And that might be a variable that I can control or not control. For instance, I might track, well, when did I last phone the customer? And I might say the longer it takes for me to phone the customer, the higher the churn. So that might be a variable that's actually in my control that I can actually influence. So basically that's what you want to drive in terms of this interpretability, is that if I've got variables that are in my control, how can I control them, and to what degree will they actually affect the outcome? So we calculate all those explainability metrics on top of all the variables to help somebody actually drive what that output will be and possibly improve as a result of that. So we calculate all of that there. And then also we bring in the ROC curve here just to sort of highlight that model's performance. And then second to the dependence plot, we also do a group dependence plot. So for instance, this is great if you want to compare one attribute with another attribute and see the specific nuance that those combination of attributes have on the model. So that's how you'd use a group explainer. So once you're happy with the way that you interpret the model and how the model's making particular decisions, you can then go ahead and deploy that model.
So just before you carry on, before you carry on, Andrew, guys, is there any questions or anything so far? You're in cricket says, I don't know if you guys are wanting to know anything a little bit more.
No, can you go to the screen again? Group classification. Group explainer.
Yes.
Can you show us an example?
Okay, so let's look at a particular example. Let's look at, for instance, checking status. Although let's look at, let's look if somebody has, okay, let's look at employment. And then basically what has to happen here is that we then train what's called an explainer, which basically calculates all the specific dependence variables against this particular deployment group attribute. And then that will allow us to then evaluate the different comparison attributes against it. So I just want to wait for that to run. So I think while we wait for it to run, are there any sort of specific questions while we wait for this to calculate?
So how do I select a model which I want to train, like after the experiment?
Okay, so perfect. So basically how you do that is there's a little button in the top right that says train. It loads a select box and you just pick your algorithm that you want.
Okay.
So that's a relatively simple process. So I think what I'll do is I'll just open a new tab and then just share that tab while that explainer is busy loading. So to answer your question, so this is a train model. Let's go back to our AutoML screen. Let's look at our leaderboard and just evaluate our different algorithms that have run. So basically, if I wanted to now train the model, I can now give it a name. I can call it credit, and then I can basically pick logistic regression. So what we do is we don't tie you into making a specific selection. Obviously, we highlight the fact that logistic regression is the most accurate. But you might want to look at these additional metrics, and you might want to evaluate a model against a different set of metrics, if that's something that you wanted to do.
So another question.
Yes.
this different algorithms that Automl tries, is a predefined thing, or it's different for different models?
So yeah, so basically, so these algorithms are generalized to the problem type. So in other words, these are algorithms that specifically deal with classification.
Okay.
So basically what we do in the background is that we basically abstract the data set to feed these algorithms the specific data set that they're looking for. So for instance, if you had to Google a cat boost classifier, the way that you'd send a cat boost classifier data as opposed to logistic regression is different. And then we handle that in the back end to actually give these algorithms the best data set that they need to make the prediction. So basically, if you look at Kaggle, you know, the one that's been really highly featured in recent time is the LGBM classifier. I think that was developed by Microsoft. That seems to be sort of winning most of the Kaggle competitions. And then also another popular one is an XGBoost classifier. So literally between cat boost classifier, LGBM classifier, and XGBoost, that's pretty much the best that you're going to get, because, for instance, random forest, XGBoost uses a random forest methodology, but just more efficiently. So so these different algorithms tend to use different techniques, and some run faster, some run slower, some achieve a little bit higher accuracy by doing certain nuances. So yeah, so each one of these algorithms has their own unique quirks, but ultimately what you want to do is you want to evaluate what algorithm actually generalizes your data the best, and you know what drives the highest accuracy. And you know that might be logistic regression or it might be LGBM, but that's the purpose of this AutoML leaderboard, is to actually assess that the model's performance. So I see the trainer is finished, so let's have a look at how this is going to look.
Sorry, did that answer your question?
So another question that I have, for example, let's say my data set has 20 variables.
Yes.
And so is it possible that I tell that these 10 variables it should include in all the model I want to run, but it can pick remaining 5 at its own will? Like for example, I have like it makes a comparison between different variables. Like it has total 10 variables and 5 are included in all models, and for other, so like for model 1 I have 7 variables, and for model 2 I have 8 variables. So can it do it itself, or I have to run another model?
Well, it depends why you'd want to do that. So obviously the model is going to pick the ones that describe the influence the best. You know, you sort of want to feed it the variables and let it do its thing. Obviously not add any additional noise in terms of variables that don't actually describe your outcome.
No, maybe let's say, for example, we have a variable, one person says maybe this is important, another person says no, it wouldn't give us any benefit.
So yeah, so you want to run that through the algorithms anyway, and then let the algorithm decide whether it found it important or not. So the algorithms do calculate what is important to it. So in other words, you know, you might as well feed both algorithms all 10, and then the algorithm will use or not use depending on what's it's finding important in that particular case. I don't know. Does that answer your question?
Yes, it makes sense.
Yeah, and I guess the other part of it is that's why the system is so unique in terms that it makes it flexible to create experiments on the fly and test your assumptions. So you might want to, in one fell swoop, run 20 different experiments and each one exclude one feature to test it if it is working or if it is more accurate or not. So the flexibility behind that is quite great, that you can choose which feature you want to exclude, and maybe you run another feature where you exclude another feature or you include something. So that makes it quite easy to do without having to recode the process.
Yeah, that's a good point. You might want to actually iterate. For instance, the best way you can improve a model's accuracy is by improving your features. You can hyperparameter tune the model all you want, but the better features you send it, the higher the accuracy will be. So sometimes what you want to do is you want to just run it through the process, let it determine what's important, and then actually focus on the feature engineering part of the data set to then actually drive higher accuracy, to say, well, focus on this and how can I improve these and these variables. So that sort of should be a real focus of the ML process, is actually getting the features in the best way that they can be. So that's basically what you could do, is you can iterate quickly in terms of AutoML, play around with certain settings, see what improves the model, what doesn't improve the model, and then sort of go back in the loop and say, well, what if I add this feature? What if I add an additional feature? And then sort of drive accuracy further and further up. I'm just sort of reloading that group explainer because something's a bit strange with that. But so I'll just give it a couple more seconds, and then if it doesn't work, we'll just have to move on. Because basically, what I want to move on to is using the model now in production, and how does that look in terms of connecting back into the database. So that should be finishing up soon.
Okay, another question I have is that all the models which it runs, they are predefined. Like, can a user add a model algorithm they want to run?
So they're predefined. So we basically cater for a set of sort of best of breed algorithms. So there would not really be a need for you to custom define a particular model algorithm. I don't see you could, I suppose, in theory, but if it's no more accurate, you might as well use the models that we cater for, and we cater for most of the models anyway. So,
but I guess what he's asking there is that if they, for their specific problem, have found in their current scenario a specific algorithm that works very well, it would be very difficult to add that algorithm to algorithm.
Exactly. We'll just integrate that into the base code of how our AutoML works, and just make that algorithm available as part of the AutoML tournament. So basically what we're going to do is keep up to date with all the latest developments in terms of the best ML algorithms, and keep on adding them to the system. But pretty much the best ones out there right now is XGBoost, LGBM, CatBoost classifier. That's pretty much the benchmark and industry standard. I see this group explainer is not working so well for me this morning. But we can sort of dive into that at another stage. But basically what it allows me to do is give me this dependence plot like this as an example, but use this in comparison to another variable. So how does credit history interact with employment, and how does that actually affect your underlying outcome? That's basically what a group explainer does. So then sort of moving on to how you'd actually use this model in production. So once you've trained your model and you're happy with everything, basically you deploy it. And what happens when you deploy it is that creates an API endpoint for you to interact with a model programmatically. So you can send that API endpoint data and receive a prediction back, or you can set up a bold prediction where you can actually point that back into your database. So you might capture all your churn information in your database, and you just actually want to update a column within that database with your result. So what OQLIS will do is it'll basically ping that table that it's trying to find the predictions on, and when it finds a record, actually pull that out and then write back the prediction right into your data, into your database, into your table. So there's no sort of need to move the data anywhere or build any custom integration. We can basically integrate right back into the database. Then thirdly, the way to interact with this is that you can actually run sort of simulations or interact with it through a form. So basically what this does is it pulls out the different columns or variables that I've defined, and then what I can do is I can basically go ahead and simulate a prediction. So what the model does is that it takes these variables and then makes a prediction based off of those variables. So right now at the default, this is classified as a bad credit candidate. But if I change these things a little bit and said, okay, I'm not a foreign worker, I'm not a single male, I'm married, and I'm 35 years old, and I've got a savings account with $500 to $1,000, and all my credits are paid, and I want to now simulate my prediction based on that scenario. In this example, my prediction is good. And then what I can do is I can go ahead and explain this particular prediction. So what happens in the background is that we run this through our explainer that calculates the dependencies of all these different variables on the outcome, and then gives you an idea of how that particular model is making a decision and what variables it's finding important. So you might, for instance, predict that a customer might churn, and for that individual prediction, we'll be able to tell you what the model is considering and to what degree to come to that conclusion. So basically, what we see over here is what's called a breakdown plot, where we can see the contribution where this model is being pushed towards the one side of the prediction, which one meaning it's good credit. So the fact that I'm not a foreign worker has pushed the model up significantly. The fact that I've got my own telephone, my own house, I've got a good savings account. So basically what this model is telling me is that these are all the variables that are contributing to the fact that I'm a good credit candidate in this example. And for instance, I went to the fact that I was a single male, and I didn't have my own phone. I was a foreign worker. I had been employed for instance, 1 year, and I was critical with other credit providers, and I've got nothing in my checking account. Let's just run this prediction and let's see what we get. So I'm a bad credit risk. And it sort of makes intuitive sense, you know, like that the model will determine that I'm a bad credit risk. It sort of makes sense against these variables. But I can then validate what makes sense to me as a person against this explainer, to then make sure that the model's actually considering the right variables in the right magnitudes. So we'll just leave this to run for a couple more seconds, and it's basically we'll pop down the breakdown plot once it's done. And then all the time what we're doing is we sort of building out sort of improvements to this process to make it quicker. So let's have a look at what this thing is considering here. So, the fact that I own my own house is great. I've got a good saving status, but the fact all the other factors basically outweigh those small positive factors. So all those other variables actually bring it down. So the fact that I'm a single male, I'm critical, all of those variables actually then contribute to the fact that I'm a bad credit risk, and I can sort of evaluate that against this explainer. And then all the time...
Andrew, like one thing that I've just noticed for the first time, and tell me if I'm correct or wrong, especially with that little graph, is that it's not close to a 50-50 split whether it's good or bad credit. It's actually quite bad. I mean, it's quite far over the nation line. It's not like you can come back and say, oh, this is maybe good credit. That's totally, the way that was explaining was totally bad credit.
Correct. So remember, a classification problem is essentially a degree of probabilities. So, for instance, 0.24 is bad credit because it's on the bottom side of 0.5. Like, so it sounds a bit abstract, but basically, if you had a scale between 0 or 1, 0 being utterly bad credit and 1 being utterly good credit, that value I just predicted was 0.24. So basically, it's telling me that I'm 80% bad credit, which is the inverse of 20% good credit. So the degree to which I'm bad is actually 80%, and the degree to which I'm good is 20%. So it's a scale of sort of probabilities that you're going to be good or bad credit. And in this example, greater than 0.5 is good, less than 0.5 is bad. That's sort of like the inflection point that determines sort of the label of the ultimate prediction. But that's essentially how classification works. So then in that process, we're tracking the number of predictions, what was the confidence intervals of those predictions, and also, once again, what accuracy we actually achieved on that model. And that's basically it. So once you've connected that to your data set or using that in the API, you're actually interacting with that model in a live way, and you basically predicting what you want to predict.
So I have a question.
Sure.
So after I have deployed the model, can I select which variables I want the model to update in the database? Like, can I
Yes.
carry the 95% interval and things like that all as well, or would only take the predicted value?
You can do both. So basically, when you actually set up a bulk API, you can say, "Cool, I want to update. I want to use my credit model as the source. I then want to, because I want to update, I need a key column because that's going to be the way that the database actually updates. So if I, for instance, had customer ID, I can pick that as a key column. Then what I can do is I can say, cool, what table do I want to update? I want to update the credit table, and then the key in my credit table is the customer ID, and then I want to update, for instance, the class, and then I want to write my prediction confidence into another column. So basically what I can do is I can set up this bulk prediction that it writes back both those values into my database.
Okay.
And then what will happen is this will just run on a scheduled basis and just keep updating your table if there's new records to score.
Oh.
Okay.
Yes.
Perfect. So any other sort of general questions? Obviously, there might be a lot of sort of technical questions or something like that if you want to ask me.
No, everything is clear till now.
What are your guys' thoughts of the system? That you guys see it could work for you? You see it as something that could make your lives a lot easier?
Yes, it looks very user friendly and like it saves a lot of coding work.
Absolutely.
Like one can save a lot of time and run different experiment models at same time.
Correct. Because, I mean, you could, for instance, do a couple of testing things in like a Jupyter notebook, but as you want to take that and actually deploy it and make it workable in like a real enterprise solution, that gets a bit tough. So those are the aspects that we've really thought about, is how do you actually scale building 100 models, and they're not all custom coded, but they're all embedded within a tool that you can actually evaluate it and manage it and make sure there's governance and accountability.
Yes.
And then all the time you can just point it to your database. You don't need to bring in any CSVs or any other strange sources. You can actually just connect it to and from your database directly.
Yes.
Cool.
Any other questions from you guys? Yeah, sorry, Mas.
Okay. So is there like you mentioned the overfitting risk in the prediction?
Just say that again. I didn't catch that.
I'm saying you mentioned the overfitting risk in the predictions. So
Yes.
so would there be a way like it can suggest that how can we avoid that issue?
That's a good point. So the reason or the way that you can improve overfit risk is you can feed it more data.
Okay.
Essentially, that's the only real way to really do it, or make sure that your variables aren't super correlated. That's one way to do it, but we don't sort of basically the overall suggestion is that if you've got an overfit risk, it means that you need to send it more data to generalize better, or you need to work on your features that it doesn't want to overfit. But that's essentially what you'll see is, for instance, I'll just wait for my screen to load again. But what you'll see is the random forest models or the random forest algorithms have a higher overfit risk than, for instance, the logistic regression, because the for instance XGBoost and LGBM that uses random forest architecture underneath it, there's a whole set of random forest decision trees that are essentially built underneath it. So what the model will then do is look at one particular scenario, and then essentially that random forest is built for that particular scenario. So there tends to be more overfit. What it'll do is it says, okay, cool, well, I've seen this scenario before, therefore apply this same function that I've seen on the test data that I got from the data. So to describe that, for instance, if we look at these XGBoost, extra trees, and random forest, these tree-based methodologies tend to overfit because I don't have enough data in my particular scenario that describes all the random nuances that would help these random forest models perform better. So what these random forest models are doing is that they're saying, okay, cool, well, here's my scenario when this and this happens. And then it applies that same scenario on unseen data, which might not be accurate, but it'll be very good on training data because it's seen that scenario before. It's got the random forest tree path built for that scenario. So it'll be more accurate on training data because it's seen it before. But it won't be as accurate on unseen data as what we see over here, because it might see a scenario that it hasn't generalized very well because it's been very specific in the way that it's built its tree structure. So, I mean, that's a lot of detail, but that's generally what you want to do is you want to feed these random forest algorithms more data to help them better generalize their structure. Otherwise, they're just going to look and say, well, oh, I saw the scenario before, therefore I just need to fit this outcome, which might not work on unseen data.